Major support for Do the Math has been provided by CHEVRON, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, Kern High School District, and AC Electric Company, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Well, good afternoon and welcome to Do the Math. I'm Michael.
And I'm Scott.
And in studio with us today we have Brooklyn. And Brooklyn, if somebody needed to get a hold of us, what would they need to do?
For math homework, help call 636-4357, toll free 1-866-636-6284. Email dothemath@kern.org. We're online at dothemathonline.net. And on social media, Facebook, Instagram, Twitter, and YouTube.
All right. Nicely done, young lady. That's a lot of ways to get a hold of us here at Do the Math, isn't there?
Mm-hmm.
Why don't you let everybody know where you go to school and what grade you're in?
I'm in 6th grade, and I go to Hart Elementary.
Have you been at Hart for a long time?
Yes.
Since?
Kindergarten.
Since kindergarten. So you're pretty used to the way Hart runs and everything like that.
Yes.
What are you most excited about for junior high next year?
I think I'm excited about having different teachers and different subjects.
So you'll like doing that instead of just staying in one classroom? You
Yes.
like going to different classes and meeting new instructors and things like that?
Yes.
Good. Well, starting next year, you're going to do that for a very long time as you go through junior high, high school, and if you go to college afterwards and things like that. So
Yes.
it'll be very exciting because you'll meet a lot of new friends as well.
Mm-hmm.
How is math going right now in 6th grade?
Right now, we're working on conversion with units.
Okay. So pints, cups, quarts, gallons, inches, feet, yards, all that kind of stuff, right?
Yes.
And have you been studying the metric system as well?
Yes, we have.
And what do you think about that?
I think I'm pretty comfortable with it, though sometimes I have a hard time with the decimal situation.
Okay. Well, you just need to remember the different spots there are, right? The different prefixes for them.
Yes.
And then it's just a matter of moving that decimal back and forth, right?
Yes.
Okay. Are you ready to do some work today?
Yep.
All right. Well, relax for a few moments because you've got a couple of minutes to rest because right now we're going to take a look at today's Math in the News. Well, today's Math in the News, we are fortunate enough once again to have a guest in studio with us. Dr. Eigenauer from Taft College is with us. John, how are you today?
Excellent, Mike. Thanks for having me.
Well, I'm certainly am glad that you were able to carve out some time for us and visit us here in studio.
It's a privilege.
You are a professor of philosophy at Taft College.
Yes, I am.
For students that are maybe not even junior high and high school yet, what exactly does that mean? You're a professor of philosophy.
It means that I get to teach young people how to think clearly. Most of all, I teach critical thinking classes, and so at our college, that means when you first enroll in college, an important skill is learning how to think critically, and that's what I get to do.
And this is something all students need to take, correct?
Absolutely. It's something that's essential for college life, and it's a requirement to move on to a four-year institution.
And how did you get into this field?
I got into this field years ago when I got more interested in philosophy because I was working in technology and changed. And when I did so, I got really interested in the ways that people made mistakes mentally. And so I learned more and more about not making those mistakes and being a more rational person. And I found it really exciting.
And one of the things I know students have been doing lately in the last couple of years is error analysis when looking at math problems. Instead of trying to figure out exactly what the correct answer is right now, what did the student do wrong? in that math problem to come up with the answer they came up with.
Right.
But you have a critical thinking course that you provide at Taft College. So can you talk a little bit about that?
Sure. In the critical thinking class, we teach students some skills that they need to prepare for life, prepare for civic responsibility, and prepare for the tasks that are coming in their four-year institution. How to create arguments, how to find errors in reasoning, things like that.
Okay, so when students are working on mathematics, how can we apply what you're doing specifically with mathematics?
Well, it turns out that there's a lot of mathematical thinking to critical thinking. For example, most people are not really very good at probabilistic thinking, at figuring out what's more likely to happen than another thing. And that ability to use numbers to figure out probabilities and make decisions is a really key element of being a good critical thinker and a rational person.
Well, I know, so correct me if I'm mistaken, and I quite possibly might be here, but let's say there's a bag of cubes, and there's 50 red and 50 blue, and a student pulls out 5, and they're all blue, right? And they keep returning it every time, but they've chosen one at a time, and the first 5 they have chosen all turned out to be blue. And the student is presented with a question, what's the probability that the next one will be blue?
Right. And the cognitive error that people tend to make is to think because 5 blue ones came out, the probability is less of a blue one coming out, which is not true.
Right.
It's still 50%. But that ability to know that the past does not influence the future is part of critical thinking.
Okay, perfect. And have you had some students that have gone through the course and have moved on and are doing some rather interesting things now?
Absolutely. I have one student who's getting her PhD in cognitive science at UCLA, another who's working as a graduate student at Harvard doing data analysis, and a whole bunch of other things from engineering to teaching. And the applications are interesting. I've had students make diagrams and take them to court and win court cases by using critical thinking diagramming.
So it is an important skill.
Absolutely. It's an essential skill.
Right.
Yeah.
And I think that people may not realize how essential it is until you actually think about what it is covering and what it entails.
Right, because it can cover the decisions that you make in life about finances and retirement. It can involve political thinking, what's best for society. It can involve health decisions, all kinds of things.
And the examples that you gave us, those are some of the careers that somebody would be, so if somebody is looking to hire someone,
Yeah.
we were talking a little bit earlier, what is one of the most important things employers want from an employee?
Employers say that in new hires, the number one skill they're looking for is critical thinking ability. And so if you go into an interview and you have the ability to even know what that is and say you had a course in it, that gives you a leg up.
Right. I can certainly see how that would. And I do want to make one comment. We appreciate all of our guests that come on and do the math, especially for our Math in the News. But I've got to tell you, in the 19 plus years that we've been doing this, nobody has had a better shirt or a more appropriate shirt than what you've got on right there.
Thank you.
Is this something that you found a while ago, or is this, I mean, I just love it.
I bought it in Paris 2 years ago.
Okay.
And I thought it would be perfect for today.
Oh, indeed it is. You know what? We certainly do appreciate you taking out some time to come visit us today.
My pleasure.
And speaking of Taft College, we were there just last week to talk about microbes and germs, and we had a little bit of that. So we can see that we had Devin out at Taft College, and we were with Greg Goling, and talking about microbes and germs and how many of those things are actually all around, and people may not realize it. And Erin was out there, and Erin, tell us a little bit about what you guys found out.
Yes, so that was actually a very interesting lab experiment. So the goal of it was, it's a biology class, and they wanted to have a Petri dish where you split it down the middle. We got a Sharpie and wrote a line, and we had it where we have pre-washing your hands and post-washing your hands. And so Devin and I, we were instructed to take 3 fingers and put it on the pre-washing sign. And then we were told to wash our hands, but we were not allowed to use a paper towel actually because there are germs on paper towels. And so to make it as accurate as possible, we decided that we had to stand there with our hands to air dry. And then once that was, we came back from the first segment, we then put 3 fingers, the same 3 fingers, this time on the post-washing your hands. And Greg Goling, who were out there that was a professor, he took those Petri dishes, covered them, and then put them in an incubator for 24 hours. And there are some pictures up here that show what happened. This is actually my hands. As you can tell, the right side is pre-washing our hands, and then the left side is post-washing your hands, and it shows the germs before and after. Now, you might be wondering, why is it that there's more germs
Right, I
on
was
the
going to
left
say,
side?
correct me if I'm mistaken, but it looks like there's more after you cleaned your hands.
Yes, yes. So what happened is that Greg explained that after you wash your hands, the water kind of opens up your pores, so the bacteria that's through your bloodstream, not all bad bacteria, it can be healthy bacteria, they are then opened up and are able to be transferred onto the Petri dish. And when that happens, obviously, it can cause more, since there's more bacteria on that side, it causes more cell division, which causes more bacteria to grow right there.
All right, let's take a look at Devin's. And that's quite a bit also. Significantly more.
Yes. And thankfully, this was significantly less than some of them that had been incubated.
And then I think, is that the last one, or do we have one more of these also?
I believe there's one more that's a side-by-side.
Okay, so then the comparison with them?
Yes.
All right.
Yes, but it was a great experiment, and it was very cool to see in person.
Well, good. Well, you know what? We thank you for going out, helping out with that. And once again, thank you to everybody at Taft College. We've had a great beginning of this season with them. First of all, with Sherry Hornbunk talking to us a little bit about Taft Talks, Greg Goling and the microbes and things like that. And then today with John Eigenauer talking about critical thinking. So we do have phone tutors available until 5:30 this afternoon. That is today's Math in the News. You ready to do some math problems, Erin?
No.
I just wanted to throw you, hey, what's going on right there? All right.
I'm good with that.
All right, you know what? Why don't you head on over this
Thank
way?
you.
Brooklyn, I think that you are now ready. Are you not?
Yep.
All right, let's take a look at one of the problems that you're working on in your book with measurement and conversions. So, Scott, here's the question. It says, how many more pounds does the heaviest soccer ball weigh? Now, the soccer ball ranges from 14 to 16 pounds. All right, so I don't know if you guys want to start putting information up there or what you want to do.
Are we looking at pounds or ounces there? 14 to 16?
Well, it says, this is going to be
in ounces?
in
there?
ounces.
Okay.
So we've got 14 to 16 ounces. So how many more pounds does the heaviest soccer ball weigh than the heaviest baseball? Round your answer to the nearest hundredth.
The heaviest soccer ball. Okay, so the heaviest soccer ball seems to me will be 16 ounces, right?
And the heaviest baseball is going to be 5.5 ounces.
Okay. 5.25. Now that my pen's working, I got to have that question one more time. What was the question again? The question is how much heavier?
So how many more pounds?
Oh, how many
because
more
we've
pounds?
got things in ounces right now, but we want to know how many more pounds is the heaviest soccer ball compared to the heaviest baseball. Round your answer to the nearest hundredth.
Okay.
So we know we will have what in the answer?
100.
Right, we're going to have a decimal in there, right? And it's going to go to the hundredths place, right? So you and Scott work on that, and then let me know when you're through.
All right, grab that pen, see what you can do. You want to grab that black one there so that we can have different colors and we'll know who's who? There you go. What do you want to do with this problem? It says how much more, right? That's the first part of the problem.
So what I'm going to do is I'm going to take 16
Uh-huh.
and I'm going to subtract 5.25 from it.
Now tell me a little bit about where you put the 5.25, because I like what you're doing there.
Because one of them has decimal, I'm going to add the 0, 0 there.
I like how you lined up those decimals. So first of all, you added a decimal to the 16, right? We all hopefully know if you don't see a decimal, it's at the end. Added a couple zeros so it has the same amount of decimal places as 5.25. Let's see your subtraction. Go ahead. All right, where's all this stuff coming from? Did you go over there and borrow from the 6 first? Oh, that's where it came from.
This one will turn into a
Okay, so you borrow from the 6. made the next column, the 10th column, a 10, and you borrow from that, make it a 9, right?
This
I
will
think
be
your math so far is
7,
good. Yeah,
And then there'll be 0, 1.
good. So tell me what that number is.
That's 10.75.
10.75 corn dogs?
10.75 ounces.
Ounces. Okay, so put that on the end. All right, and I'm pretty sure it said how much more, right? We found the how much more, but the next part of that question was how many more
Pounds.
pounds? This is not in pounds.
No, it's not.
What do you want to do next?
I have to convert that to pounds.
Okay, that's a great idea. How do you do that?
That's what I got confused with.
Okay. So we need some conversion factors, right? That's kind of
Yeah.
what you're working on in class. Do you know off the top of your head how many ounces are in 1 pound?
16.
16 ounces in a pound? Okay, so that's going to be helpful, right? It's a helpful number. What do we do with the 16 and the 10.75? How about this question? You can answer this one for me. Is this amount of weight, 10.75 ounces, is this more than 1 pound or is this less than 1 pound?
Less than 1 pound.
Okay, so at least when we get an answer, we better get a number less than 1, right?
Yes.
We're going to get a decimal. And that's why I think the question asked you to talk about rounding to the nearest hundredth. So we're going to have a decimal less than 1. The number in the ones place or the units place is going to be a 0, right? So we know
Okay.
that part. So what do you think? Add, subtract, multiply, or divide that we're going to do with 10.75 and 16?
Divide.
I think let's do some division. I think that's a great idea. Yeah. And if you had to divide, which number would you have the outside and which number would you have on the inside to make sure your answer was less than 1?
I think I would divide 16 by 10.75.
Okay, let's set that problem up and let's see what happens. We know the answer's got to be less than 1, so that's good.
Can I take off this?
Sure. Oh, you wanted it to go away? You got to go the other back side of it.
Use the
Where?
eraser.
Use the eraser part. And I'll go over here and write what you got. 10.75 ounces. That was the difference. Okay, so we're going to set up a division problem, right? And which number is going to go on the outside?
6.
Yeah, 16 on the outside. I think that's a good idea.
There?
Let's make the 16 go on the outside. I thought that's what you said anyway.
So 16 would
16
go
on the
here.
outside, yeah. And then divided into 10.75. And we'll see if at least, sometimes these computers, no matter how much we work with them, they kind of go crazy, huh? Mm-hmm. And hooray for erasers, pencils or computers. All right, 10.75. Show us what you're going to do here. Uh-oh, hold on. You can put in a bunch of X's. What happened? Tell me what's going on in your head there. at least.
16 can't go into 1 or
Okay.
10.
Okay, so does that mean we have a 0 in the ones column?
Yes.
That's good, right? That's what we wanted. Okay, good. So I like the X's, but can you go ahead and put a 0 there on the second X, just so we know it is a 0, just like we talked about?
Yeah.
There you go. Put a 0 there. And now you want to go 16 into what number?
107.
I'm sure you know that in your head, right?
No.
Let's try 6.
Let's try 6. That's a good guess. Okay, so put a 6 up top there. That was our hint for the day.
6 times 6 makes 36. So the 6 would go here.
Good for you.
3 would go
Oh,
here.
I like what you're doing here.
6, 7, 8, 9.
Uh-huh. And we'll do some subtraction and hope we don't get a number bigger than 16, right? Oh, we got 11. That's pretty good. Okay, you gonna bring a number down for us? Yeah. Okay, so you know 16 times 6 is 96. Do you think you can get another 16 in there without going over? I think you can.
Yeah.
I think so. So why don't you try a 7 up there instead of a 6 for the next one? There you go. Yeah, I think we can squeeze one more 16 in there.
7 times 6 makes 42.
Good for you.
And 7 times 1 makes 7 plus 4 makes 11.
11. Boy, we were close. That's pretty good. 3.
3.
Do you think we want to go one more place? Because we have to round to the nearest hundredth. You have the 7 in the hundredths place, but that 7 might stay a 7, or...
But we have to have something in the thousandths. So
I
we
like
can
the way
round.
you think. That's exactly right. You got to have some in the thousands to be able to round it. So bring down that 0. Good idea.
It can only go into it once because 15 times 2 makes 30.
Good for you. Yep. So it can only go one time. You can finish the problem if you want to, but you probably don't even need to because we just know it's a 1 and you're going to use the 1 to round it, right?
So Because the 1 is less than 5, I'm not going to mess with that number.
That's right. And I'm going to put this little wiggly equal sign because that means approximately. So we're going to round 0.671. What is it going to round to if you round it to the nearest hundredth?
0.67.
Can you write that next to my squiggly equal sign? 0.67 ounces, right? No, not ounces. I was joking you. Because we had ounces before. What did we change it to?
Pounds.
Pounds, there you go. You know the abbreviation for pounds? LBS, because there's no L or B in pounds, right? That's important to know. Really well done. I like the math you did there.
Nicely done, you guys. So hopefully that helped you out with that measurement and conversion problem right
Yep.
there, right? All right, go ahead and erase the board for us.
If you want to go way down to the corner, you
He's
can make
going
a
to
new
do it
one.
the easy way. Circle it all and
Yeah, that's fun too.
zap it out of there. And
Well done.
so, Brooklyn, come on over here for a quick moment. Do you have any idea what today is?
Today is the 3rd
Correct. Of,
November,
in the year,
2020.
and how old are you right now?
I'm 11.
Are you old enough to vote?
No,
How old do you have to be?
you have to be 18, I believe.
That's correct. You have to be 18. Used to be 21, but a number of years ago, they moved it to 18. And so today, so you can see Scott and I, we both have our stickers on that we voted, right? So do you know why Election Day is today instead of some other day?
No.
Any, like, why would you guess? Like, if you could say, we're going to have Election Day on this day and this is why,
Would
When
it
do you
be
think you would have
because today is the day that President George Washington became president?
excellent, excellent, excellent theory right there.
Like
Like,
the
hey,
way
you
she's
know what?
thinking.
When the first president became president, that's the day it was, so that's the way we're going to have it from now on. And the funny thing is, the first president,
George Washington?
Washington, was not Republican or Democrat. He was independent because he believed there should not be parties like that, and he was an independent. But here's the story about why Election Day is on this day. All right? So, hundreds of years ago, society was an agrarian society. You know what an agrarian society means?
No.
Agrarian has to do with agriculture. Okay, so they would grow things, and then in November they would harvest the crops. Okay, and they said that in 1792 a law was passed where you had to have all state elections completed during a 34-day period that would end up the first Wednesday in December. Everything had to be finished, but you had the 34-day window in order to do this. Okay, now that was when people traveled by foot and by horse. Railroads and telegraphs made things easier to get communication around, okay? And so they decided we need to change this, tighten it up a little bit. So they said, what day of the week should we have the election on? And they said, well, not Mondays, because you don't want people traveling by buggy on the Sabbath on Sunday. So we can't do it on Monday. And you can't do it on Wednesday because Wednesday was market day. So the farmers would not be able to make it on Wednesdays. So that's why they decided that Tuesday would be when Americans would vote. And in 1845, they passed a law that presidential elections would be held on the Tuesday after the first Monday in November. So think about what I just said. The election is going to be on Tuesday after the first Monday. So do you know why they said that? What could possibly happen?
There would be different people who weren't able to vote.
Could be. Think about if December 1st or November 1st was a Tuesday, right? There was no Monday in November, was there, yet? So
No.
the 1st would be a Tuesday, and they don't want that. So it would then happen on the 8th because they have to wait for a Monday to happen. So the first Tuesday after a Monday is when the election would happen. So that's why it's today, because we already had a Monday in November, and this is the first Tuesday after that first Monday. Make sense?
Yeah.
I
Kinda
think it
weird
would
how
make more
they all
sense to
came about
Kaylin
this.
if you said the first Tuesday after Halloween, right?
Anyway, so that's why we do vote on today. We do have phone tutors available until 5:30 this afternoon, as well as most Tuesdays and Wednesdays throughout the regular school year. We'll be back with more right after this. Some of the students may be looking at this going, all right, we've got the flaps, the aileron, the wing. What do we have on the ends over here?
Okay, all this is what's called static wicks. Okay, as this airplane flies through the air at 400 to 430 knots speed, tremendous amount of static electricity, especially in clouds and in rain and snow. So this airplane builds up a tremendous amount of static electricity. We got to get rid of it somehow. The airplane is designed to be able to carry that through, and it literally exits the airplane through these static wicks. And then you come around to the wingtip, and what you see here is the lighting system, and we have different colored lights for each wingtip. The left wingtip is red, the right is green, and the back is white. So when I see lights coming at me at nighttime, I know what direction the airplane's traveling at.
Now, as far as lights, I know that we're not on a runway right now, but there are lights on a runway, and are there different colored lights, and why would they be different instead of just white lights?
Yeah, it's the runway lights where you take off and land are white.
Okay.
Taxiway lights where you actually taxi to the runways are blue. Okay, and as you get close to the end of the runway, the lights that are supporting it start turning red. Okay,
Letting you know you're getting close to the end of this.
You're running out of distance, or hopefully you're getting the airplane stopped. Now, this particular airplane is fairly sophisticated, and we have a single point fueling system on the other side of the airplane. So we can take a hose, hook it up to the airplane, and it pumps fuel and feeds all the fuel tanks. But if that system was to fail, or the truck didn't have that capability, we can still come and fill the wings right here over the top of the wing, okay? The 1,000 gallons of fuel is held in both wings entirely. So it's hard to believe, but these wings will hold that volume of fuel. And it actually goes down to the bottom of the airplane, and it's where it pools together, and that's where fuel pumps for the engines and that type of thing, and all the electronics to measure the amount of fuel that's on the airplane. Very important for us to know exactly how much fuel we have.
Right.
It's what's so interesting, you know, and the bigger the airplanes, the more sophisticated, the more fuel they have to carry. Like a 747 actually carries fuel in the horizontal stabilizer of the airplane. And they use it, 2,000 gallons, believe it or not, fits in the horizontal stabilizer of a 747. And they use that fuel to help balance the weight of the airplane as they're burning fuel off.
Now, what's the difference in octane between the fuel that you would use in these planes as opposed to
a car?
Another vehicle?
Okay. We have two different types of fuel. We'll talk about aviation, but it kind of relates to cars too. Cars use gasoline. Piston airplanes use aviation gasoline. But when it comes to turbine-powered airplanes, jets, all the jets the airlines fly, this particular airplane, turboprops, they all use Jet A, and that's a kerosene-based fuel.
Okay.
It doesn't have the high octane rating. It's a heavier fuel. It's harder to ignite, but puts out more energy, and it's supposedly cheaper to buy. So anyway, we have this whole airplane ready to go. When the passengers get here, we load the baggage in the back. There's a baggage compartment. They get up in the airplane, they sit down, and we shut the door, start the engines, and we take off. They're in the back talking business and doing whatever they want to do.
About anything else
And they don't worry about anything else. And then in 2.5 hours, we have them in North Dakota, and they're taking care of business as they go.
Good. Well, let's take a look inside.
Okay, perfect. Lighting system here. These are the engine controls here for the power. With these two throttles full forward, we're producing over 8,200 pounds of thrust.
We just love aviation here at Do the Math and Do the Science. We do have phone tutors available until 5:30 this afternoon. Time now for a visit from our friends from Science for Kern. All right, and our Science for Kern Challenge today, we've got Jamie in studio. Jamie, how are you today?
I'm doing well. How are you?
Good. Nice to see you. And if somebody wanted to get a hold of some materials from Science for Kern, where would they need to go to?
You can go on www.scienceforkern.org, and right now we are doing distance learning packets, so you can email me or you can visit the website, tell me which kit you would like to do, and we can get that so that you can send it out to your students and they can do science at home.
All right. Well, you've got Brooklyn over there, a 6th grade student from Hart Elementary, so you guys take it away.
All right, thank you. So what we have here is, this is an easy thing to do at home, and it's super fun. And so our supplies that we're going to use is what we use salt. You want a clear straw, so no colored straws, no straws with stripes on it, and then some food coloring. And so what we're going to do is, we're going to get to that experiment in just a minute, but we want to go understand why are we doing this type of experiment and what's going to be happening. So we can do that by looking at this jar right here. So believe it or not, I created this jar almost 20 years ago for my class. And so what it's showing you is we have some different stuff in there. So what can you tell me, or what do you notice about that jar?
I noticed that the two different liquids, it looks like there's two different liquids in there that aren't mixing, or there's just something in the liquid that's dropping to the bottom.
Okay, and what do you notice in the middle?
I noticed in the middle there's a ball that's not sinking or floating.
Right, and so if I picked this up and moved it around, does it change any of your notices about it?
No.
No. What do you wonder on what's going on in that jar?
I wonder if there's something at the top that's blocking it from moving around differently.
Okay. Well, this is a concept, and in science we call density. And that's why I created this, is so that we can understand the density of objects. And in second grade, we start to learn about physical properties. And physical properties, density is a physical property. So it kind of tells us what that material is. Okay? So we are going to use that thought process on density, and we're going to make a colored straw. And so we have 3 different liquids here. And what you're going to do is, I want you to show everybody at home on how you pipe a straw. So we're going to take a straw, and then you can use the red, I'll use the yellow. We're going to put the straw into the color, and then put our finger on top of the straw, and then pull it out. Okay, and we have a color. All right. So what we're going to do next is, I want you to experiment. Each one of these colors has a different density. Okay? With these different color densities, they're going to layer different colors in that straw. But if you happen to try 2 colors and you do the density is wrong, they're going to mix. So what you want to do is, you want to try and create a rainbow. So what we can do first is, let's try the yellow in the red. All right, and I want you to try and see if you can layer the 2 colors. And then here is our trash. So if it ever mixes, we're going to put it in here so that the colors do not change. So go ahead and try it out. All right, so she's trying the red first.
And then what do? Just put it in there?
Right, so now you're going to go into the yellow, and you're going to go further down so we can start to collect yellow. So go all the way down. Okay, then pull it up. Okay, so then let's let that go. So you notice that there's a little bit of yellow at the bottom. Okay, let's let it go. This time what we're going to do is, you just barely put your straw in the red.
Okay.
There you go. Put your finger on it. Then let's go further into the yellow. There you go. Let go of it with your finger. Suck it in. Put your finger back on top and pull it out. Did it layer it?
No, it's
Look at it, you got a
to
little bit of rainbow, huh?
But it's starting to mix.
It is. You know why? Because you're turning your hand sideways. There you go. So now they're straight up and down. All right, so now you figured out the 2 colors. Let's add a 3rd color in there. So you're going to be using the same amount you put in the straw, and try it with 3 colors. Do you remember which color was on the top on this one?
The top one was that one.
Okay, so let's try it.
I think I'm going to do this one, then this one,
And then go further in. There you go. Pull it out. Ooh, what happened? Do you see any yellow in there?
No, they mixed.
Okay, let's try it again. What would you want to try? There you go. Then go further down. Yeah, let's
Now
try it
there's no
again.
green.
When you were in this one, notice that you let go of it, and we got colors in it, but that's okay, we can keep going. So let's try it again.
What if I do this one first this time.
Okay.
And I'll do this one. Then I'll do this one.
Oh, wait. Notice that you have the red and the green.
Mm-hmm.
Do you remember which one was on top when you did it before?
Yellow.
Was that on top of this one?
I think I might have put a little bit less than that one. I
Okay.
can try it again.
Let's go back and try the red. There you go.
This one?
Okay, try it. Go down and try it, and let's pull it out and see. All right, let's not turn it sideways. So now we notice that we know the red is definitely on top of the green, right?
Yeah.
So let's try that yellow. Go down further. Let it go. Come back up. And now we have the yellow.
Mm-hmm.
So what do you think is going to be your first color?
I think my first color should still be red.
Okay, so let's try that.
'Cause
What
it's
do you
been
think
the
the
one that's-
second color should be?
I think now my second color should be yellow,
Mm-hmm. And then your third color.
green.
Okay, so let's try that. Go further down. There you go. Go to the next one. Further down. And let's bring it out. Look at that. Got it. It looks beautiful. All right, so let's put that back in there. So let me tell you about what I did with these colors. In this one right here, I just added water and red food coloring.
Mm-hmm.
In this one, I added just a little bit of salt and some yellow food coloring. In this one, you can kind of still see there's a lot of salt in there, huh?
Mm-hmm.
And I added a lot of salt. So what do you think is going on when you looked at those straw, the
I
colors?
think the salt is causing a chemical reaction
You think so?
between
Okay.
the food coloring.
Okay. Now, this is physical properties, so there is not chemical, you're not looking
Yeah.
at chemicals reacting with it, but we did create a different compound with that. So what we're trying to understand here is we had different amounts of salt, okay?
Yeah.
And this creates densities. So when we looked at it and we looked at two basic colors, okay, we know that the bottom one is more dense than the top.
Yes.
Okay, and then if I go into the green, what happens? The green becomes more dense than all of those.
Mm-hmm.
Okay, so then let's go back to this. So from that information we got from there, what can you say about this green water at
think-
the bottom?
This one has more salt than this one.
Okay, there's no salt in it, just to let you know.
Yeah.
But we can say from this and learning about density, what
It
can we
has
say
more
about it?
density there.
There you go. How about the ball?
I think the ball's in the middle because it has in-between density, kind of like how the yellow had.
Right, okay. And then what do you think about, this is baby oil on top.
I think the baby oil had less density like the red did.
Right, there you go. That's great. Now let's think about things that you see every day. What about if you buy a soda and you see ice on top of your soda? What does that tell you about the ice?
The soda has more density.
There you go. That's great. Hey, we're learning a lot over here.
There you go.
That's great. Thank you so much, Brooklyn. And this is just a basic concept of density. And we definitely want to experience that and learn that in the science classroom.
All right.
And that's it for Science for Kern today.
Nicely done, Science for Kern. Thank you, Jamie, for coming down. And Brooklyn, I'm sure you learned a little bit about density over there today, right?
Great.
There we go. We'll be back with more right after this.
All right, students, this is Buzzy from Camp Keep. And as you look at the scene before you, can you guess what we're going to be focused on today? What's the first thing that pops into your mind? Good. Waves.
Hey, this is Buzzy from Camp Keep. Have you ever wondered what it's like to be in the waves? What causes waves? Well, today we're going to learn. is a wave.
But let's back up a moment, because what is in fact a wave? The definition of a wave is a disturbance of one or more fields that oscillate repeatedly about a stable equilibrium. Now that's a mouthful, but the word I love is disturbance. So it's energy moving through, and if you took all the energy from the waves of the ocean, only 2% of that would be enough to power all the energy for our needs as humans. Now, one thing to keep in mind, the water isn't moving, it's the energy moving through what is causing the wave. But what of other types of waves? Do waves only occur in the ocean?
There's microwaves.
And there's infrared waves.
Ultraviolet waves.
There's gamma waves.
By the way, there's X-ray waves as well.
And there's radio waves.
But our focus today are the waves of the ocean, of which there are 3 major types. The first is the tsunami, which is caused by a geologic disturbance from an earthquake, a landslide, glacial falling, or even a volcanic eruption. The second is the tides, which is caused by the gravitational pull of the moon and the sun. And you can think of the tidal shift as one big, long, sweeping wave. The last category is the one we're most familiar with, and that is the most common. Can you guess what kind of types of waves these are?
So there are a lot of types of waves, but what we really want to focus on today, because we're here at the beach, are the ocean waves, which are also called wind waves, which should give you a hint about how ocean waves are formed. And I have a cup of water here, and if I blow on the top of it, there's ripples that form, all right? And that's basically what's happening way out in the ocean there. There's wind generated, and that pushes the waves towards the land, causing them. Now, when it pushes it, there's a couple different things that are going on. So this is a wave going up and down, and the top part of the wave is known as the crest. Okay, that's the top part, and then when it goes down, that is called the trough. All right, and then can you guess, what do you think the distance from one crest to another would call this distance right here? Any ideas? We call that the wavelength. The wavelength, one to the other. And then the wave height goes from the trough right here to the crest. Okay, that is the wave height. And then this is the wave length. Notice this is a right angle. All right, these are known as transverse waves, and versus sound waves that travel kind of parallel, transverse waves travel at right angles.
So we know that these waves travel over great distances thanks to storms out in the ocean that are generating wind. But how do they ultimately break on the shore? What's responsible for that? The shape of the rocks or sand underneath the water, i.e. the sea floor, is known as bathymetry. And this is responsible for how the waves break. The friction of the water meeting the land causes the waves to collapse. In this diagram, you can see where the bathymetry is steeper, the waves crash closer to shore and are larger, whereas the smoother bathymetry causes waves to be smaller. The last term I want to share with you is called the period, which is a measurement of time as the wave moves from crest to crest. I'd like to end today by giving you a little quiz to see if you can remember some of the terms that we learned about today.
All right, Camp Keep, always some great things going on over there. Now, Hart Elementary, have you guys done your Camp Keep thing yet this year?
No.
Do you know if it's coming up?
They think we're probably going to do it in the middle of March when we normally would have Camp Keep.
Okay, right, because I know that some schools have done it virtually right now.
Yeah.
And they've done those kinds of activities, but who knows, by the time March rolls around, you may actually have an opportunity to possibly go over there and experience it like that. So anyway, we do have phone tutors available until 5:30 this afternoon. The phone numbers are at the bottom of your screen periodically throughout the program. And Brooklyn, you had fun with that science activity.
Yep.
Did you learn a little bit about critical thinking from Dr. Eigenauer today?
A little bit.
A little bit. You're getting well-rounded today, aren't you?
Mm-hmm.
Well, you know what? It's time for you to get back to work. Are you ready?
Yeah.
All right, back to work, young lady. Here we go. So you're still working on measurement and conversion in your 6th grade math book. So I've come up with another problem for you, something a little different than what's in your math book, but still related to it.
Yeah.
We don't want to just do the problems you do in your math book all the time. So a customer wants to cement an area 8 feet by 16 feet by 4 inches deep. All right, now think about this for a second. Okay, you've got something 8 feet long, or 8 feet wide, and 16 feet the other way, and it's about 4 inches deep.
Mm-hmm.
Can you think of anything that might represent in real life? Like, can you think of something that might be that size?
Maybe a sidewalk block?
Yeah, part of a sidewalk, right? Maybe part of a driveway or something like that, right? So this is something that actually happened. This is something really you're going to apply what you learned to, all right? Since cement is measured in cubic yards instead of feet and inches, okay, we want to turn each of these dimensions into yards. So why don't we go ahead and write up the dimensions first. We have 8 feet.
Do you want me to draw a cube?
You don't need to.
You can just draw the numbers.
Right, so we'll go 8 feet, then we have 16 feet, and we have 4 inches. And I want you to turn each of those into a yard, or turn them into yards, however many we need. So talk to Scott first, explain what you're going to do first, because he needs to figure out what's going on here.
8 feet can convert to yards by dividing by 3, because 3 feet is in 1 yard.
3 feet in a yard. Okay, I like where you're going with this. This
So
is a
the
good idea.
same thing would go to that, and I feel like the same thing would do for the inches.
Okay, let's start from the top, and we can keep talking about it. Wonderful. So you're going to do 8 divided by 3. Is that what you're doing there?
Yeah.
Okay. And 3 goes into 8 2 times.
And then
But it
it
didn't
leaves
quite make
2.
it. Now, we could have a decimal here, but I'm just thinking, with my little bit of math experience I have, I'm pretty sure it might work out a little bit better if we use some fractions.
Mm-hmm.
Okay, can you make this remainder into a fraction instead of dropping down a 0 and adding some more zeros and keeping on going?
I could put it 2/3.
There you go. Good job. So 2 2/3, right? That's the whole entire mixed number.
Mm-hmm.
If you were going to change 2 2/3 back to an improper fraction, can you show me how to do that real quick? So way over here to the right, way over here, can you do 2 2/3 and change that to an improper fraction? Oh yes, the old times plus.
6, 7, 8.
And tell me what the result is. What is that answer?
8/3.
8/3. Is there a different way you could say that with addition, subtraction, multiplication, or division? What does 8/3 mean?
8/3 means 8 feet out of 3.
8, but tell me addition, subtraction, multiplication, division. 8
Divided
by 3, and that's what you did, right? That's exactly what you did. So using that example, you could see that your fraction you make at the very beginning, 8/3, you did a division problem out of it, and you came up with 2 2/3. Can you use that reasoning, that logical reasoning, right? Just like we talked about at the beginning of the show, to do your 16. What would the 16 look like in a fraction, first of all?
The 16 would look like,
Aha, good place to start. 16/3, which really means 16
divided
by 3. So now you can do that part. So does 3 go into 1? Nope. 3 goes into 16 though.
3 times 5 makes 15.
Good, and don't forget to make this remainder in a fraction, okay?
Into 1/3.
Third, yeah, 5 1/3. Do you think we should check it to make sure you get back to 16?
Yeah.
Okay, let's check it real quick, just to make sure. Just to make sure it ends up as 16/3. 5 1/3 times plus. Okay, so we're feeling pretty confident about the first part, and we're feeling even more confident about the second part because we have some experience and you checked it on your own. Good job. What about the third part? Tell me a little bit about 4 inches. What has changed in this last part of the problem?
The inches is smaller than a foot.
It is, that's right. And so tell me why in the first 2 parts of this problem you divided by 3.
I divided by 3 because 3 feet is in 1 yard.
3 feet in a yard, and we're changing to yards, right?
Yes.
How many inches are in a yard?
There are 36 inches in a yard.
There you go. So we're not going to divide by 3 this time. Instead,
We're going to divide by 36.
that's it. You got it. So can you set up that fraction for us?
It would be 4/36.
That's it. Now, go back to the beginning again. 8/3. Was that number bigger than 1?
Yes.
That was. What about 16/3? Was that number bigger than 1?
Yes.
It was. What about 4/36? Was that
It's
number
not.
bigger than 1? It's not. So it's going to be a pretty small number. You could work it out with a division problem, but you're probably going to end up with a decimal, right? Something that's really small. So why don't we just take that fraction that you have, since our other problems ended up as fractions too, can you just go ahead and reduce that fraction for us?
4/36
What would you divide each one of those by?
by 4.
That's it. Good idea.
One ninth.
That's it. And can you go right over there at the 34 on the bottom there and make that into 36? Because you wrote a 4, but I know you were thinking 6, and you certainly got the right number there. All right, the last thing before we finish this up. Remember the problem asked us to change these all to yards, right?
Yeah.
So let's go way back up here when you had your 2 2/3, right? Way up here.
Wait, where? There.
Yep. The 2 2/3, and just put a yards after that, right? 2 2/3 yards. What about the other one? You change that to 5 1/3 yards. And what's the last one?
Yards.
Yards. Yeah, that's what we wanted to do, right? 1/9 of a yard. And that, like you said before, that was actually less than 1. So I like the way that at the end of this problem, you change your conversion factor because the units of the problem actually changed, right? Great work on that one. Nice job.
Wonderfully done.
Yeah.
All 3 of those. All right, for your great work so far today, you've got yourself a meal courtesy of our friends at Broken Yoke. So congratulations on that. You feeling pretty good with measurement and conversion?
Yes.
Good. I've got another wonderful problem for you, young lady.
You
Here we
knew that
go.
was coming.
Go ahead, erase the board.
The whole thing. Well done.
So now we're going to go to the metric system.
Aha.
So, how many grams of salt, NaCl, would you add to a liter of water to make up a normal saline solution, 0.85% or 0.85 grams per 100 milliliters? So, is there any information that you know right now Because if we set this up kind of like a proportion, it might make it very easy to do. Okay, so is there anything that we can set up right now that we know?
85 grams per 100 milliliters.
Okay, so 0.85. So let's go ahead and put 0.85 grams is to 100 milliliters. So if we have 0.85 grams in 100 milliliters of water, we need to know how many grams we need for a liter.
Oh, okay.
So we need to go from what you've got to a liter first of all, and then figure out how many grams would go in that.
So to convert 100 milliliters to liters, I'm going to find out what I should divide by. So
Good for you.
King Henry died making dark chocolate milk.
Okay, tell me a little about what you just did there, because there's a whole bunch of letters there that came out of nowhere, but it looks like you really know what you're doing, so I didn't want to stop you.
This is what I use this as a King Henry died making, but I use a question mark because it could be liters, grams, anything.
That's the main
Dark
unit of
chocolate
measure.
milk.
Okay, gotcha. So that's how you can go back and forth. And every time you go one to the right or to the left, what do you do mathematically?
When I go bigger, I divide, and when I
Okay.
go smaller, I multiply.
Wonderful. Okay, so what's your plan here? You're going to change the 100 milliliters to what?
Liters.
Okay.
So this is milliliters. I'm
Yep.
going to divide by 2, 3, so 100,
Okay.
which makes
Wait,
1
how many
liter.
times did you move it over?
I moved it over 3 times.
Gotcha. So you're going to divide by 100
Mm-hmm. And
or 1,000? How many zeros does 100 have?
100 has 2, so
2.
1,000.
So really, you're going to divide by 1,000. There you go.
So
let's take your
100
100.
divided by 1,000.
So here's an easier way kind of to
Uh-huh.
do this, because you're going to end up with a weird number here, all right?
Mhm.
Get rid of that real quick. Let's just put 0.85 over 100. And how many milliliters are in a liter, do you know?
1,000?
1,000. So put equals next to that. And let's put 1,000 on the bottom. And that will help us get to how many grams we need on top. So if you went from 100 to 1,000, what did you do?
I divided. No,
Well,
I
to go
multiplied.
from, you're going to multiply by what?
By 10.
Good
Right.
for you.
So you're going to do the same thing to the top.
So
You're going to move that. There you go. Perfect. 1 decimal place, and you get 8.5. Nicely done. Perfect work. All right. Brooklyn, great job today. And until we meet again, continue to do the math.
Major support for Do the Math has been provided by CHEVRON, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Bakersfield West Rotary Stroop Family Foundation, Panama Buena Vista Union School District, Bakersfield City School District, Kern High School District, and AC Electric Company, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.